Hi, this is Bernard Brault, and this is a third video of a series that I'm making on music and specifically tones and how you combine tones. And I sort of came out as to why we have 12 notes and not 13, 15, 12 chromatic note, including the flats and sharps if you want. Okay, so it started with something very simple with a single tone, and I used the 440 hertz tone, which we call the A note. And one thing that was fundamental is that a tone combined with any of the multiple of its frequencies or harmonic is a note. So that remains the same note with different harmonic content if you want. And then the next thing was what is the next nicest tone that you can combine with the original frequency. And what I found was another tone that has 50% or 3/3 of the frequency. Basically, it combines very nicely because the peaks and zero crossing sort of interact with each other in a beautiful way. And what came out of that was what I'm showing here. Was the first note was 440 hertz, and I multiplied by 3/3, and then it came out with this series. And eventually, we sort of circled back to the original note, but with a little bit of an error. If you look here, I'm back to the original note, but it's 446, or if I want to keep it twice the frequency, dominantly would be 892 and not 880. But yet, what was really interesting out of this sequence is that, I basically rediscovered the circle of fifth, what musicians call circle of fifth, and here it is. So it makes a lot of sense because this would be the next nicest tone to combine and so on. But surprisingly, that's what sort of came out of it. And then I put the tones or the different notes together and looked at the frequency that they would have. And for example, the first A would have 440, the B flat 470, and so on. And I realized there was this problem about the, I guess, going back to 446. And the frequency curve looked like an exponential. So I matched an exponential across, and that's what you see here in blue versus in orange. So it is almost an exponential, but when you actually match an exponential, you don't have the issue of falling back into something a bit different. All right, so the first two videos covered this. So this third video here is I realized that maybe there are other tones that you can combine that would interact very nicely with this one versus the tone that is 3/3. And the next best thing to 3/3, right, is something that is 33% or a third higher. So 4/3 as opposed to 3/3, 4/3. So if I generate a second tone here, right, and I've got 440 hertz times 4/3 it doesn't come up with a round number, but it comes up with 586.666. And here's the generated tone. I'm going to zoom into it to have a better view of how they could interact with each other. And as you can see here, I'm looking at the first zero crossing. Not much interesting there. Not much there. But look, the third zero crossing is the same for both. And you look at the next one. So it looks like every third zero crossing will match, right? Except on this one, this guy is going down and this guy is going up, and the second one, they're both going up together, right? So that's I think that's the next most interesting thing. So let's see what they look like when we combine them, and I'm pretty sure it's gonna make a nice new tone, and here it is. So as I described before, here they're sort of like this is the first zero crossing, and they're sort of start to cancel each other, and then the next one they're sort of like generating a higher peak because they're both rising together. And look at this nice beautiful curve. So this was the next best tone, and the first one was times 3/3, second one is times 4/3. So let's go back to the spreadsheet here, and more or less let's redo what I did here was, you know, generate a second note. Notice that note number 2 here is not going to be the same. Instead of like times 1.5, or it's going to be times 4/3. So I'm just going to use a little bit of a formula here. So it's equal to this times 4/3 right there. And I'm just going to push this out all the way to the end here, and then have this one equals to this one divided by 2. And repeat the formula up to here and see what happens. Okay, so what we have here, again, we're back to, you see here we started with A note, 440 Hertz. We have 12 notes altogether. And then here we're back to the first note. But this time around, you see, we're a little bit off again. Remember, like the first time we were off up by 6 Hertz. Interestingly, here we're down by 6 Hertz. And here's the sequence, and we're back to the A note after like you know, circling around or iterating this. So I'm going to make a pause here. What I'm going to do is rank them and see how they rank, and based on the ranking, because the ranking tells me the name, right? It goes like A, and the next thing after A is a B flat, and then B, and so on. So I'm going to rank these notes and see what the sequence looks like. All right, so I'll be right back. Okay, so I filled up the table, and as you can see here, of course, we started with the 440 here. And this was multiplied by 4/3, 4/3, 4/3. But then I wanted to see what was the next sequence. So in terms of pitch, so 440. The next note, note number 2 here, fell here because it's 464. That's the next higher up frequency to 440 is this 464. And of course I get this by divided by 2. And then the third one, which is we call B, and that's just a convention. The third note, 488, and then the fourth note is a C, and so on. So I identified all the name of these notes that I basically generated times 4/3, and I found this pattern A, D, G, C, and surprisingly, again, you know, remember the last time when we did this, I sort of recognized that this was a circle of fifth. If you look here, it was A, E, B, and this was a circle of fifth going clockwise. But look at this new combination here. Again, we're in the circle of fifth, but this time around we're going backward. We're going counterclockwise. So I'm going from A to D, G, right there, G, C, F, and so on. So the next best combination of two tones, you know, where the zero crossings will be very, very, you know, nicely aligned with the original tone. The next best one to this first one also generates a circle of fifth, but it generates a circle of fifth in the reverse direction. And somehow I think musician will recognize this right away, that, you know, I found that the adjacent note to A was E, and they'll say, yeah, of course, this is like a really important. And then the next note to A here is D. And certainly A, E, D is sort of like, I don't know, that's the basis of rock and roll and blues and so on. So this is really interesting. What else is interesting is I look at the frequencies here this time around, right? So the first time around I came up with these frequencies, and if you remember, when I reached the very end, it was off by 6. But the frequencies are not quite the same here. If I look at the first note, of course, it's the 440. Now the second note is down here, 464. Using the 3/3 method, the second note that I had was 470. And this time around, the second note is, where can I find it? Number 2 here, 464. So you see, by using this sort of 4/3 method, and that's why I called it 4/3 tuning here, I get 440, 464, 488, and so on, and all the way down. Of course, I have the same problem as I had in the original video. where once I get the octave higher, if I use this number here, I'm going to get 868, and all of a sudden this is not going to be twice the frequency. But this time around, the upper number is 6 Hz lower than what I expected, and this one was 6 Hz higher than what I expected. And actually, if I look, I rounded these numbers, and if I just expose a little bit of their value, you see they're not exactly 446, but let me expose these values a little more, right? So 4 digits, and I said, well, that's kind of interesting. What if I were to add these two and see, because this one is 6 higher, this one is 6 lower, and what would happen if I look at this frequency here and add it with that frequency right there, and I get 880 Hz. Slightly off, not exactly 880 that I would get with equal temperament, but certainly a lot closer. And using, I guess, the average value between this guy and this guy, because if I average them out, then I divide by 2 here and divide by 2, I would get so close to 440 by this time around. I'm not off by 4 or 5%. I'm very, very, very close. So that, I think the 3/3 tuning here generated, something that, was sort of very harmonic and all that. The problem I had was, going to the second octave. I had to cheat here. And then I came up with the equal temperament, basically fitting an exponential curve through 2 points, the 440 and the 880, and coming out with this equal temperament. And then I got this 4/3 tuning here. And of course, this number up here is this, well, I should pluck. And then here's this is where I would cheat. But if I could come up with sort of like, I don't know, an in-between tuning, an average tuning between the two, and with the nice thing that I don't need to cheat here at the 880. I do get 880. So close that it's off by, 0.01%, 0.01%, and not 1%. So this is it. I don't know if I'm going to discover some more stuff, but I certainly discovered 1, 2, 3, maybe a fourth way of actually tuning or creating different frequencies for the scale, and this is kind of interesting. And out of this exercise, came out the 2 most important adjacent notes to the A note, of course, being E and being D. And E being a little bit nicer, and I think that's the reason why you look at music, progression and scale progression, and they tend to go, if you start with the A scale, you're gonna like go back A and D there, because remember the D one here was kind of important. It was like had a really nice relationship with the 4/3 frequency. But then musicians tend to stick with this one and then just sort of evolve here and go between the D and moving, progressing into this sequence here, as opposed to progressing in this sequence, for the basic reason that this is, was probably a little bit of a nicer tone. And let's see if I can figure some other stuff out. But so far, I thought this was kind of interesting. Thank you.